but I can do it. So mean free path, diffusion, and effusion. All right. Effusion, which is probably a word you haven't heard of. Effusion refers to a gas that goes through porous solids. So that means little holes. The gas squeezes through little holes, so it's not a tightly sealed container. Now, how fast the gas leaches out through these little holes depends on how fast the gas is moving. Velocity. Can't write. Molecular velocity. Speed. If it moves fast, it is going to both diffuse, which we're not talking about, and effuse first. Diffusion is going from higher concentration to lower concentration, just moving on out. So if we keep the temperature constant, that means we're not changing how fast they're moving. At a constant temperature, what's going to move faster? Big molecules or small molecules, which we just figured out up here? Small molecules, yes. Small molecules move faster. All right. So let's use this principle. If we have four choices, hydrogen, nitrogen, helium, carbon dioxide, hydrogen sulfide gas, which one is going to move the fastest? These are molar masses. Hydrogen, yes, because it has the smallest molar mass. So hydrogen. Then what? Helium. Really, it's just a matter of counting up and putting these in numerical order. Hydrogen, then helium, then what? Nitrogen. Then what? H2S, hydrogen sulfide. And lastly, carbon dioxide. Just put them in order of molar mass. The smaller one moves faster. That's what we decided. One more equation here. This is called Graham's law. I will give you this equation. I've successfully navigated life without having to memorize Graham's law. You do not have to know it. All right. It says here, rate of gas A over rate of gas B equals the square root molar mass B over molar mass A. So let's define what these are. Rate A and rate B are the effusion rates. So that's going to be in a speed. Capital M's are the molar masses, which I don't like because I think a capital M is molarity. But they didn't ask me. So, what do you notice here when you look at this about gas A? Are they on the same side of the fraction? No. A's in the numerator here, the denominator over here. So that means it is inversely proportional or related. So this tells us this goes along with the same concept, faster rate, lower molar mass. Higher molar mass, slower rate. But you have to deal with the square root. All right. How the guy actually came up with this, I don't know. He had too much time on his hands. Now, a lot of times you can use this in several ways, but it'll give you a ratio, so you can use it to calculate the molar mass, or you can find ratios. Now, because these are both rates, it's not really going to have a unit, because it depends whatever the speed is. So most of the time these problems are going to say unknown gas effuses at a rate that is 0.462 times that of nitrogen. All right, at the same temperature. What that means is we're gonna have to make this a fraction. So we're talking about our rate. So we have to define what is going to be gas A and what is going to be gas B according to our equation. That's the tricky part here. So it says 0.462 times that of nitrogen. So in this case, our rate of the unknown over the rate of hydrogen, because the unknown is 0.462 times, this is an N, nitrogen. And it gives us what this ratio is, which is nice because you don't have to calculate them. So we can go ahead and use the rest of our formula. So nitrogen is gas B, gas A would be the unknown. So molar mass nitrogen, molar mass of our unknown. So from here, it is plug and chug. All right, it's a little bit complicated mathematics, but it's given this. So our rate of our own to the rate of hydrogen is 0.462, right? That's what the problem tells us. Square root, molar mass of nitrogen, because this is N2, so it's going to be 28 grams per mole. And then we got to solve for this unknown. All right. So this is just math. So we're solving for this. If you would rather put it as X, that's fine. What should we do first? Square it. Square it. All right, so we're going to have 0.462 squared, which is a long number. That's not really going to matter. I'm going to go over here because I'm running out of space. So 0.213 equals 28 grams per mole over molar mass of the unknown. Now what should we do? Yeah, multiply this. So we get 0.213 molar mass of your unknown, 28 grams per mole. If you can do this in your head, you don't have to write it down. Divide. So molar mass of the unknown, what is 28 divided by that? 131.2 grams per mole. Look at your periodic table in the noble gases. Which one is it? xenon. So you can identify an unknown gas if you need to. Now let's go the other direction. This is asking us to find a ratio of the rates for hydrogen and krypton. Don't worry, we're almost done. All right. So let's make, it doesn't tell us which one is which. So is everybody okay if I make this one gas A and this one gas B? We're okay with that? All right. So we know rate A, rate B equals square root molar mass B, molar mass A. Again, that equation will be given to you. So we have hydrogen and we have krypton. So we know rate hydrogen, rate krypton. It wants the ratio, so we're going to get one number here. Square root. So now we need molar mass of krypton, which is 83.8. 83.8 grams per mole. Hydrogen gas, we'll go with 2.02 grams per mole. Look, the units cancel. It's so beautiful. All right, what do we do first? I'm going to divide first. If you take the square root, you got to take the square root of both of them. So I'm going to divide. I'm going to do 83.8 divided by 2.02. So we're going to say our ratio equals the square root of 41.49. No units because our units canceled. Now I'm going to take the square root. So our ratio equals 6.44. That tells us that hydrogen effuses 6.44 times faster than krypton. That makes sense because hydrogen is smaller. All right, now we did all of that assuming that kinetic molecular theory, we made those three assumptions. Guess what? It's not really true. Here's how things are different. So, but we go with it anyway because it's the best theory we have. So we still use it, but we know that there's error involved because real gas particles actually have a volume because it said the size of the particle is negligible, meaning it doesn't matter. Well, it does, because it does actually has a volume. So if it's at high pressure, so they're really, really compressed, they're actually going to occupy a rather lot of the total volume of the container. Because again, high pressure, squish it down. Think about crushing a Coke can. That means we've got PV equals nRT. At high pressure, so when pressure is really high, high pressure, the volume, what we predict by the ideal gas law, is going to be too low. So the actual volume, the real volume, is higher. So at really high pressure, volume is higher than what you calculate. So it has to do with pressure and volume. Now, real gas particles do not collide elastically. They don't just ping pong off of each other and lose no energy. Energy is lost, you got to pay the tax. So real particles actually do interact with each other. They interact with each other a whole lot when it's really cold because they're moving slow. So when they hit each other, they're going to not bounce off as fast. So we say that the particles are going to be sticky. They're going to be really sticky when we're at low temperature. So since they're really sticky at low temperature, our ideal gas law has to do with the pressure. The pressure is actually lower than what you calculate. These are lab kind of simulations. We're not going to be doing things in our lab. We can't generate pressures that high. We cannot generate temperatures that low.